All right. So good morning. Today we will start with chapter 4, but before that, let's have a quick review of what we did with chapter 3. In chapter 3 class, the focus was the first discussion was on partial market equilibrium. Pag sinasabing partial, there's only one commodity, and with that, we only determine the equilibrium price and quantity of one good. We also acknowledge that that model is quite limited because in reality we are confronted with a lot of commodities, and so we try to extend that one from a one commodity to a two commodity equilibrium analysis, and then which we again tackle with what we call a general market equilibrium analysis. So again, it talks about two market commodities. We determine price and quantity into two goods, and somehow, although it's still limited to two commodities, uh, it's still quite a helpful concept given that there is still an extension, given that we have looked at the relationship between commodities, whether they're substitutes, whether they're complements. Okay, and right, if we want to also class in the two market commodity, we have come to realize as well that we have worked with 12 parameters and at most 6 equations, including the equilibrium conditions. So by given with that, nasasabi natin na medyo complicated na. So we introduced the concept of writing it alternatively using shorthand method, but still it was still a bit onerous. So imagine class if we try to include in the model all the commodities in an economy and in one comprehensive model. So it tends to get more onerous, it tends to get more complicated. But there is a discipline. No, there is a whole subject devoted to it, which deals with what we call a Walrasian type of general equilibrium model. So this is a more sophisticated, more complicated of introducing those all commodities in one model. But again, as far as our level is concerned, we will only be dealing with two commodities. But perhaps if you'd like to work on Walrasian class, you can always do that in graduate school. But in our case, we'll only discuss two functions of prices in two commodities or quantities as well. But again, in general, when dealing with n commodities, we can still express that one. We can still go back to the basic and express that one into demand and supply functions. And also, we introduce the same equilibrium concept or the condition that should be no excess and there should be no surplus in those set of n equations. And again, in Seguro, we can still work with three equations using substitution and elimination method. But when you're dealing with n simultaneous equation, medyo mahirap na siya. So we need to develop a new method, a new way to arrive with equilibrium values. And so today we'll be dealing with what we call a matrix algebra. Again, it's an easier way compared to just dealing it with substitution and elimination method. Great. Okay. Now, for simultaneous equation models class, again, there is a systematic method of testing a unique solution. So particularly dealing with equilibrium analysis, unique solution to get equilibrium price and quantity. But then again, matrix algebra is not only limited to equilibrium analysis. So in totality, we just refer it as solving for that unique solution. If we're only dealing with matrix algebra, if you're only dealing with linear models class, we have the concept of what we call a determinant. If you're dealing with a nonlinear model, then we will later on will require the knowledge of partial derivatives and what we call also Jacobian determinant. Okay, so for chapters 4, For chapter 4, we will only deal with first the linear models and then extend it to later on with the Jacobian determinant. Let me just go quickly, class, with what to expect in chapter 4 and 5 as well. So Chang and Rainwright, class, they kind of wrote this one into two parts. The first one is introducing the basics, meaning what are the elements that are necessary to come up with with the unique solution. So mostly the elements present, the operations present that we will be using uh, in dealing with matrix algebra. So that would be in chapter 4. Again, I said this one in my earlier class. It might seem a bit disorienting at first because we're trying to define every element before we go to chapter 5. Chapter 5 kasi is already the part where we introduce Kramer's method. We also introduce inverse matrix, where that is already the parang method of solving unique solution. Okay, so the element consisting those process are found in chapter 4. The method, the process of solving is in chapter 5. Okay, so uh, um, in as far as the course goes is concerned, class, I think that 4 and 5 is quite where the parang the new concepts are coming in. So I mentioned before that there's really nothing new in the course, but 4 and 5 is perhaps an exception, given that in there is no introductory course on into this one. Perhaps in other students who have subjects in math. I think you've dealt this one, but I think in econ, siguro this would be the first time that you'd be dealing with matrix algebra. So again, we will be dealing it one by one in terms of concepts and elements, but we will wrap it all in chapter 5. Okay. So my goal really is just to understand per topic, per term, and then we can move forward. Okay. All right. So again, today we'll be discussing linear models and matrix algebra. If you'd like to follow the discussion, we are in chapter 4 in Chang's and Reinhardt's book. Okay. For a while. Let me just get my notes here. Okay. All right. So let's go to this presentation. Okay. All right. Now, as an introduction to this chapter, class, when we're dealing with linear equations, such as for this one, okay, so this is what a typical linear equations look like. We can try to define it more specific to a matrix notation by defining 3 ingredients. So these are your coefficients, unknowns, and constants. So if we would try to rearrange that one into a matrix notation, we'll have to remember 3 things in that notation. We have coefficient, unknowns, and constants. And for instance, class, a sub 1 here, so I'll just call this one a1, but again, a sub 1. This is the coefficient that is attached in the first equation. No, this is the coefficient in the first equation attached to the variable x1. Okay, so this is again your coefficient. These are your unknowns. You might find me interchangeably using the term unknowns and variables from time to time, but again, just referring to that, what we're trying to solve. Okay, so this is your coefficients. These are your unknowns, the same as also coefficients, unknowns, and these are your constants. So something that we do not solve, something that we take as given in a certain if we're dealing with models. Okay. So, right. Again, this is A12 or A sub 112. That is the equation attached. That is in the first equation attached to the variable x2. Now, right. So I'll just skip this part already because I think this is just an introduction to linear systems. But in a more general form, class, if we deal with, again, dealing with simultaneous equations, it more or less consists with m equations and n unknowns. In our example, in an example before, yung sa general equilibrium analysis, yung two commodity model, there are how many equations for that? Excluding the equilibrium conditions, there are around four. So four kasi supply demand functions of one good, demand and supply functions for the other goods are there around four. In that case, it resulted to around 12 parameters. Now, again, class, this is more on the general form of the linear system with m equations and n unknowns, and it can be written this way. Okay, so let's pay attention as well. One thing also in matrix algebra is that it's very specific, it's very technical. Technical in a sense that you have to know the importance of writing it in looking at the coefficients because say for example aij, so I is particular to one location, j is also particular to a placement or location. So again, it's better that to remember what aij is. For example, a11, so I'll just be casually saying it as A11, A12, A13, A21, A22. So when I refer it as A11 class, that means that it is in the first equation, it is in the first row, first column. Okay, and A11 is a coefficient that is attached to the variable x sub 1. Okay, let's also have A22. So A22, looking at aij here, so I is row, j is column. So 2 is the second equation. Sorry, let me repeat that one. 2 is the for the second row, and another 2 here is would be the second column. So that would be A22. That is attached to the variable x sub 2. Okay, and so on and so forth. In our study class, we will only be dealing with until A31. So A31, A32, and A33. But then again, if we will have numerical examples later on, I think it would be also good to remember what A11 is. Because again, we keep on dealing with a lot of numerical examples. So again, if I deal with, when I say A11, we have a specific location for 1, 1 there. Okay, and that is attached to the variable x sub 1. Okay, so just adding to the three things earlier, these are the coefficients. These are the placement of the coefficients, the order. These are the variables x sub 1, x sub 1, x sub 2. And depending on how many equations do you have or and unknowns, you have x sub n. So these are our unknowns and our variables. On the right side of the equation, we have our constants. Okay. By the way, class, let me know if I'm a bit too fast in the discussion or if you have questions. I think it's best to ask the question per topic. Okay. Because if not, I'll just go ahead and move forward with the slide. We'll go to the other slide. What else? Okay. Now, if you're dealing with simultaneous equations class, we're interested in the following questions. Does a solution exist? If yes, how many solutions are there? Is the solution unique or it has infinite solutions? In our example, in equilibrium analysis, we are just concerned with a unique solution that is a similar notion to equilibrium price and quantity. So most of our study here in chapter 4 deals primarily with getting the unique solution of that equation. Now, as you all know, there are 4 ways, or there are other ways of solving linear systems. The first 3 are the ones that we discussed in chapter 2. That is again graphical analysis, but we all know that this might be impossible, not really impossible, but it takes more of our time. But again, still helpful. Substitution, elimination. It might not be appropriate again when dealing with a lot of parameters and a lot of equations. So that's why we now resort to what we call a matrix method. So by definition, Matrix algebra, it's a method of solving, or it's a more suitable method for handling large system of simultaneous equations. It is a compact way. So later on, we will be rearranging some equations. But matrix algebra class is helpful because it is a compact way of writing all those set of equations. Number two, it gives you a method to test the existence of existence of a solution with the use of a determinant, which we will again talk later. And it's also again it's a more it's a compact way, and it saves time as well. Okay. uh a matrix is simply a rectangular array of numbers. A matrix with m rows and n columns is called an m by n. Also class, I will just be casually referring it to m by n. So if I mention m by n, then I'm dealing with what we call a dimension. So most of the time, palagi kong binabalikan, ano ba yung dimension ng matrix na to? So m by n is row always precedes the column. So it's always rows and columns. Rows first, columns after. Okay, so that's row. That's row and column. Okay. We'll go back to the okay, so all right. Now with this one class, two matrices are equal if they both have the same size and if the elements in the two matrices are equal. Example, example here would be matrix A has elements 4, 3, 2, and 0. Matrix B has elements 4, 3, 2, and 0, and therefore they have the same dimension. They have the same rows and columns, which is a 2 by 2, and the elements present in those matrices as well are the same. I'll go back to this one quickly, class, but I think it is just a good description, a good example to this description. Okay. All right. Moving forward, we have there are three types of ingredients in the equation system. We have a set of coefficient, we have also a set of unknowns, and we have vector of constants, or we have constants. Usually we just denote this one as matrix A depending on the label, matrix A, B, or C. In this example, that is matrix A. Matrix A consists of coefficients. Matrix X here consists of the unknowns or the variables, and sometimes it's called vectors of unknowns. And we also have a matrix for constants here. Okay, now let's try to rearrange them into a matrix notation class. And then an example here is this linear equation. So we have three equations here. We have the first equation, 6x sub 1 plus 3x sub 2 plus 3x sub 3 equal to 22. So rearranging it rewriting it in a matrix form, ax is equal to b. That is 6, 3, 1. We also include the signs. So that's 6, 3, 1, 1, 4, -2. We have 4, -1, and 5. So this is 6 is A11, 3 is A12, and so the placement there should be properly defined as in position of A12. So the placement are again fixed and they cannot be changed or altered, because if they do, you will arrive with a different answer. Okay, so bakit nga siya fixed class? Kasi nga all the coefficients as attached to x sub 1 are on the first column. The same goes for all the coefficients attached to the variable x sub 2 that is in the second column, and the same goes for the coefficients attached for the variables x sub 3. Okay, so again, coefficients for matrix A here constitutes 6, 3, 1, 1, 4, -2, and 4, -1, and 5. So that this is the matrix. These are the arrays for coefficients. Let's go to X class. So X is again what are we looking for in the model? What we are trying to determine in the model here. So again, we have three unknowns. So we will need to solve, or we will need to look for three numbers. No, that is not right. We need to look for three unique solution that is identified for x sub 1, x sub 2, and x sub 3. D class would be our constant. So again, it is easy. It's actually easily detectable because it is on the right side of the equation. And aside from that, it has no variables attached to that. So particularly, it could be a constant. So a constant, again, we do not solve that one, and we take that one as a given. So again, in other economic text class, it's written as AX is equal to B or Bravo. But in Chang's and Rainwright's book, I think they're consistent that they wrote this one as AX is equal to G. Okay. All right. Okay. Now, aside from that class, so it's a more general. This one here again refers to rewriting a simultaneous equation in matrix form. So again, this is the matrix form or matrix notation. AX is equal to B. We also have other terms here which we call as vectors. So pag sinasabi mong vectors class, the dimension, it's very specific to a dimension. You have a column vector. A column vector is a vector that is a vector that has only one column. Example, kaya tinatawag siyang vector of unknowns kasi it's a column vector. Okay, so again, a column vector has a dimension with only one column. So in this case, vector of unknowns is a 3 by 1, meaning there are 3 rows here and there's only one column. The same for vector of constants. You have 3 rows here and 1 column. So one thing to remember again of a vector is that it's either a column vector or a row vector. A column vector, only 1 column. So with that idea, you have a row vector here. It's usually denoted by a prime symbol. That is, again, there's only 1 row. The dimension for this one is it's a 1 by 3. Okay, there's only 1 row, and regardless of how many columns columns that is, a row vector has only one row here. Okay. All right. Questions, guys, before I proceed to the next one? Let me also check my notes if there's something that I've also overlooked. Okay. The members class, again, as you may have already noticed, the members in the arrays or the elements that belongs into the arrays, they are enclosed in brackets. Another usual practice is that there's also enclosed in double vertical lines. But I think in our practice here, in our study, we will just limit siguro in using brackets to connote that that is a matrix. Okay. Okay, so I think I mentioned this one late kanina, but I just want to emphasize that the location of each element in a matrix is unequivocally fixed by the subscript. Every matrix is an ordered set. So again, very specific, A11, we refer it to a coefficient belonging to the first equation attached to the first variable. So that is in the first row and first column. Okay, so again, if I refer to A11, sometimes I just refer it A11, A12, A13. So I'm referring to the coefficient. Okay. Question, class, before I proceed? Okay. Now, by the way, class, as you can see in the matrix notation, nakikita natin that AX here, so AX, there is a need for us to perform some operations. Okay. And if you look closely, we need to multiply matrices A here with matrix A here with matrix with the X matrix A, we need to multiply matrix X A here with vector of the unknowns. Now, with that idea, let's introduce matrix operations. Okay. Okay, so, all right. But before that, class, this is not part of the operations, but this is again the description. Okay. So two matrices are equal if and only if the dimensions are the same and they have the elements corresponds in the locations in the array, meaning they have the same location. Example, for matrix A, we have elements that are consist of 4, 3, 2, and 0. The dimension is also a 2 by 2. For matrix B, the matrix consists of elements 4, 3, 2, and 0. The dimension is a 2 by 2. We can say also that because they have the same dimension, which is a 2 by 2, and the placement of the elements corresponds to the same location, then both matrices are equal. For matrix C, A is not equal with matrix C here because even if they have the same dimension, the elements are not the same. The placement of the elements are not the same. Okay. So again, this is not part of matrix operation, but a description of the matrices. So let's go to let's go to the operations class. So just also a similar concept is we can perform addition, subtraction, and multiplication of matrices. But for division class, there's a question there, so we need to a lot more time to discuss to it. But for now, let's discuss those that we can easily perform. Okay, let's start with addition. Two matrices can be added if and only if they have the same dimension. For addition, the conformability, the condition that needs to be satisfied is the two matrices should have the same dimension. Okay, let's look at the first example class. So for in the first example, let's label that one as matrix A. So matrix A here is a 3 by 3. It has 3 rows and 3 columns. Can we add that one to matrix B, which has 3 rows and 3 columns? Yes, we can, because again, they have the same dimension. How do we add two matrices? That is A11 plus B11 or A12 plus B12. In this example, that is 3 plus negative 1, 4 plus 0, 1 plus 7. Okay, 6 plus 6, 7 plus 5, and 0 plus 1. So again, I mostly remember this part in general terms. So that is A11 plus B11 or A12 plus B12. Let's also look at the second example here. So in this second example rather, we cannot perform the addition with these two matrices because in this matrix, it has the dimensions. The dimension is a 2 by 3. For this matrix here, the dimension is a 2 by 2. So clearly, class, the dimensions are not the same. So therefore, we will not be able to perform addition with these two matrices. Question? All right. Sige. All right. For subtraction class, for the subtraction for the operation A minus B there, it can be similarly defined if and only if A and B also had the same dimension. Let's look at the examples here. This matrix, the dimension is a 2 by 3. In this matrix, the dimension is a 2 by 3 as well. So both we can perform subtraction in these two matrices, again, because they have the same dimension. So how do we subtract 0 minus 2? So A11 minus B11 or A12 minus B12, that is 1 minus 3, negative 1 minus 1, and so on and so forth. Right. As I think the discussion, the only thing that you need to remember for addition and subtraction is that the dimension should be the same. Okay, right. Now, if there's no question about these two operations, let's proceed to multiplication. The thing about multiplication is that you need to remember there are parang two kinds, I would say, or two, no, two, they're different, so they're not ways. So there are two kinds in multiplication. In multiplication, we have scalar multiplication. I mean, we also have matrix multiplication. Let's go to scalar. So scalar class, that is to multiply every element of that matrix by the given scalar. So scalar, it's a one entity, one number. So that is denoted by k there, and you will need to multiply that to every element in matrix A. So the easiest to remember for scalar multiplication, that is Ka. Okay, K stands for the scalar, and A stands for the matrix itself. So that it means that K would be multiplied to every element in matrix A. Here's an example. There are two examples here. So that in first example, we have a scalar 3. So we will need to multiply that one to every element. Okay, so as you have noticed, class, there is no there's no dimension that needs to be dissatisfied in order to perform scalar multiplication. What is only needed is that you have a scalar, and you can also the scalar can also be a negative number. So let's look at the example again here. We have a scalar 3. We multiply it to every element. That is 3 times 0, 3 times 1, 3 times negative 1, 3 times 4, 3 times negative 1, and so on and so forth. We also have another example. We have a scalar 7. Scalar 7 multiplied to every element in the matrix, in this matrix. So that's 7 times 3, 7 times negative 1, this and that. So again, as the scalar class can be a negative number. Now, tinatawag siya na scalar because it can scale up or down every element in the matrix. Our example here for 4, it scaled up to 12 because of the scalar. For negative 1, it scaled down to negative 3 because of the scalar as well. So a scalar has this, performs this parang scaling down or scaling up the element, okay, or the element in that matrix. Question, class? I think we need first to establish if we've understood the first three before I go to the matrix multiplication, because it requires more analysis for matrix multiplication. Question? All right. All right, that's okay. So makikita niyo, class, that the discussion is a bit straightforward. So we're just trying to define and try to be technical every now and then. But the whole parang analysis part would be in chapter 5. Okay. So if there is no question, I'll go to multiplication of matrices. Okay. So yung multiplication of matrices, class, it has a dimensional requirement, or we can just say it conformability condition that should be met. And the way to go, class, is first to remember what is in those two matrices. Ano yung lead matrix, and or what is the lead matrix, or what is the lag matrix. Example, this one here would be the lead matrix. This would be the lag matrix. So what is the conformability condition here? The conformability condition states that the column dimension of the lead matrix should be equal to the row dimension of the lag matrix. Let me repeat. The conformability condition in order to perform matrix multiplication is the column dimension of the lead matrix should be equal to the row dimension of the lag matrix. To simplify, let's look at the dimension, class. That's why we need to do it as a practice to keep on writing the dimensions below the matrices to have that parang immediate way to check if if that would conform or with that would not violate the condition at all. So these two should be equal. Column, the column dimension again of this matrix here, which is the lead matrix, should be equal to the the row dimension of the lag matrix. So 2 is equal to 2, then we know that we can go ahead and do the matrix multiplication. What is the product of these two matrices? We look at the row of the lead matrix and the column of the lag matrix. So the product would be a 3 by 2, which is confirmed in the product here. Okay, so let's look at muna again by step. Let's look at if the dimensions are conformable. Okay. All right. Example here. This is again more a general form of saying it, which I again more comfortable of just parang memorizing. So again, if A here class has a dimension of an m by n, B has a dimension of a p by q, then the conformability condition states that n should be equal to p. The product would be an m by q. If matrix A class has a dimension of a 2 by 3 and a matrix B here has a dimension of a 3 by 1, then the row of the lead matrix should be equal the column dimension of the lead matrix should be equal to the row dimension of the lag matrix. The conformability correction, this should be a 3 is equal to 3. Okay. The product dimension, so since the conformability condition is equal or is not violated, we can go ahead and multiply the two matrices. The product dimension would be a 2 by 1. Okay, because again, m by q, so that would be 2 by 1. All right, so since there is no question on the dimension requirement, which I think is we have defined well here, let's go to how two matrices are multiplied. Let me just go quickly class of the example. Okay, let's have it here. Great. All right. Okay. So let me share again my screen. Okay. So going back to this slide here, how do we multiply matrices class? There are quite a lot of ways that you can do it. I think I'm just sharing what I'm accustomed to or what I'm comfortable with. You can find your own parang a way of doing it. But this is how I multiply matrices. It's by row, column, row, column, row, column. So in all the analysis that I do, it's always row, 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 and then column, column after. So again, that's row, column. Example, for this, because we know that the product dimension is a 3 by 2, it will need to consist of 6 elements in the matrix. So the first element, that would be A11. So that would be the coefficient in the first row, first column. That is a sum of the two matrices, two products. So that would be A times A, small letter A times capital A, plus B plus the product of B and C, capital C. And so
Ma'am, you're on mute po.
okay, thank you. So I think we left with, again, matrices multiplication. So again, that is row, column. That's how I do it. Let's have numerical example, class. Okay. Supposing you have these two matrices, matrix A is equal to, consists of elements 1, 2, 3, and 4. Matrix B consists of elements 0, -1, 6, and 7. So let's have a quick exercise to get the to arrive at with the product of A, B, and BA, and why the placement matters, why the location, no, why the definition of lead and lag matrix is crucial, class, in arriving with an answer. Okay, so I'll pause the recording and then let's have a quick lang siguro exercise. Okay, so with that activity, the answers are reflected on your screen. For AB, the elements are 12, 13, 24, and 25. For BA, the product for BA is -3, -4, 27, and 40. Now, I mentioned earlier na you need to have a practice that the dimension should be written below the matrices. But as you can see here, it's easier to detect because you know it's a 2 by 2. Okay, because you know that two matrices are 2 by 2. But then again, still have the practice na to write the dimension, because you'll later on, you'll have more examples consisting of dimensions that are not the same. So you will need to look for that. With our exercise today, you will also notice that the lead and the lag matrix are crucial, again, in arriving a correct answer. So pag sinasabi nating lead and lag matrix, dito, matrix A is the lead matrix. Matrix B here is the lag matrix. Okay. The same for B. For B here, the case is yung lead matrix is matrix B na, tapos yung lag matrix is matrix A. Okay, so parang the placement or the position does matter when dealing with matrix algebra. Okay. All right. So I think all of you got the correct answers. Let's try one more time, class, before I proceed to the next one, which is the question on division. For this example, it might take a bit of time. So, but we'll wait for you. So, supposing if you have a matrix A here and matrix B, and this would be our lead matrix, and this would be our lag matrix. So first, try to check if it does not violate the dimensional requirement. And second is determine the product dimension. And third, determine the product of the matrices. Okay, let's pause the recording and let's take a few minutes from the recording. Sharing with you again the file. Here we have dimension. So this is what I mentioned earlier, that let's have it a practice to have the dimension set or written after every or below the matrices. So we have a 3 by 3 and we also have a 3 by 2. So the exercise that I asked was supposing we have a lead matrix A here and a lag matrix B here. So we know that by looking at the dimension, we have AB is conformable, meaning it satisfies the dimensional requirement. But we also know, which also Estrada also indicated, that PA is not possible. Okay, so because PA is not possible because the dimensions of the lead matrix for the column, the dimension of the column, the column dimension of the lead matrix is not equal to the row dimension of the lag matrix, which is again in the case for BA. So let's start with the exercise for AB here, and the answers would be this one. Okay, so I hope you got the same answer, class. The answers for the elements for AB here consists of 0, 2, 36, 20, 16, and 3. I hope you got the correct answer. I'll be posting again this file here to give you a more time to do the exercise. Okay, but I think that yeah. So anyway, I think that we've somehow managed to. There are 1, 2, 3, 1, 2, 3, 4, 4, or I'll plan to add a fifth presentation. So We still have 5 presentations for chapter 4. We've only discussed the second part, but that's fine. Let's just take this one slowly because again, we're still building on the foundation for chapter 5. Right, so I think we'll end up the discussion here, and then we'll go back to this presentations on Friday. So that would be right, but wait, let me just